Hello friends, I welcome you in lecture number 21 on Laplace transform. From last two lectures we are discussing about inverse Laplace transform, and our goal is to reverse all these formulas which we have discussed for Laplace transform. So in lecture number 20 we have taken the inverse process of standard Laplace transform formulas. Now we are going for different results which we have discussed for Laplace transform, like first shifting theorem, multiplication by t raised to n, division by t, Laplace transform of integral of a function. We will reverse all these formulas for inverse Laplace transform. So we start with first shifting theorem. We know that if Laplace transform, for example, function cosine of bt, suppose Laplace transform of cos bt, we know that it is s divided by s square plus b square. Then by first shifting theorem, Laplace transform of e raised to at cos bt can be obtained by replacing s by s minus a in this Laplace transform. So here we simply replace s by s minus a and we obtain Laplace transform of e raised to at times cos bt. And by the definition of inverse Laplace transform, because this is the Laplace transform of this function will be inverse Laplace transform of s minus a divided by s minus a square plus b square. This is equal to e raised to at times cosine bt. So we don't have to remember this formula for inverse Laplace transform. We should remember this first shifting theorem. And if our function given can be written in this form, then we can use this formula to obtain the inverse Laplace transform of that function. Another formula we can develop is using this Laplace transform of sine function. Suppose we consider Laplace transform of sine bt divided by b, then this is going to be 1 divided by s square plus b square, and therefore by first shifting theorem, Laplace transform of e raised to at sine bt divided by b, this is equal to, we replace s by s minus a square plus b square. So therefore inverse Laplace transform of this type of function, 1 divided by square of s minus a plus square of some another constant, this is equal to e raised to at times sine bt divided by b. So if it is possible to write down our function in this form, then we can use this formula. So in this lecture we will discuss some examples related to these two formulas, and here I have written these two formulas which I just discussed. Okay, fine. So we find out inverse Laplace transform of these functions. First function is 3 divided by s square plus 6s plus 18. So if there is no s present in the numerator, here in the numerator s is absent, so this suggests us to use this formula, L inverse of 1 divided by s minus a square plus b square equal to e raised to at sine bt divided by b. If s was present, then we have used this formula for this sine function, cosine function. S minus a over s minus a square plus b square has inverse Laplace transform e raised to at cos bt. But if s is absent, then we will try to convert our function in this form. Now here if we observe this denominator s square plus 6s plus 18, then I have to write this as square of s minus something plus square of something. So for that I can decide the last term of this second degree polynomial in S. For that we can use this formula. We know that square of middle term is equal to 4 times first term into last term. We can consider S square as first term, this as middle term, and we require last term because this last term does not allow me to write this as a square of something. So for that I decide the last term using this formula. Last term must be middle term square divided by 4 times first term. Here middle term is 6s and square of 6s will be 36s square. 4 times first term is s square, and we obtain that s square will cancel out and 4 into 9. So if last term was 9, then we can write this as square of s plus 3, s square plus 6s plus 9. So for that we can rearrange this. We can write instead of 18, we can write 9 plus 9, and we will be able to write our function in this form. So I am writing, I will start from this step. This is just rough work for deciding the last term, and if you can decide without doing all these things, then it is fine. So s square plus 6s plus 18, this I can rewrite as 3 divided by s square plus 6s plus 9 and plus 9. I am writing 18 as 9 plus 9. I write 3 outside and I write this as 1 divided by square of s plus 3 plus 9 can be written as square of 3. So I am writing in this form. So you can compare with this, value of a will be minus 3 here. If we compare with this, a is minus 3 and b is 3. So now I can use that formula. So I apply Laplace inverse on both sides. L inverse of 3 divided by s square plus 6s plus 18. This is equal to 3 divided by L inverse of, I can write one more step. I can write s plus 3 as square of s minus minus 3 plus square of 3. So now I can compare with this formula. L inverse of 1 divided by s minus a square plus b square. If you compare with this, value of a is minus 3 and value of b is 3, and the formula is e raised to at sin bt divided by b. Here we take a equal to minus 3 and b equal to 3, and this is there. So e raised to a equal to minus 3 sin bt, that is sin 3t divided by 3, and 3 will cancel out and we obtain e raised to minus 3t sin 3t. So in this way we can use this formula to obtain the inverse Laplace transform of this function. So whenever you have irreducible second degree factor, then you can use this formula or the formula for cosine function. So you have to write down your function of second degree in this form. Try to write your function in this form. If you cannot write directly, try to search for last term using this formula. We consider another example. Here we have s plus 3 divided by s square plus 6s plus 13. So first step we will do is we will try to search for last term. Here last term 13 does not allow me to write this as a square of something. So for that I find out last term. Last term equal to middle term square. Middle term is 6s, square is 36s square, divided by 4 into first term. So here also last term must be equal to 9, but here we have 13, so we will split 13 as addition of 9 and 4. So first we write this as s plus 3 divided by s square plus 6s plus 13. I write here s square plus 6s. I require last term to be 9, so I write 13 as 9 plus 4, and this is s plus 3. Now again I can write my denominator as square of s plus 3. S square plus 6s plus 9. 4 can be written as square of 2. And because I have s plus 3 here, and I can observe that in the numerator also I am having s plus 3. So I can use that formula corresponding to cosine function. L inverse of s minus a divided by s minus a square plus b square. This is equal to e raised to at cosine bt, and we can compare. Value of a is minus 3 and b is 2, so this is e raised to minus 3t cosine of 2t. But of course I have to write on the left hand side L inverse, therefore L inverse of s plus 3 divided by s square plus 6s plus 13 equal to L inverse of this function, and using this formula we write L inverse of this function as e raised to at cos bt with a equal to minus 3 and b equal to 2. So here in the numerator I am having s, and first I write my denominator in this form, and then I check whether s plus 3 is present here or not. If s plus 3 was not present here, then I have to rewrite this in another form. Suppose my numerator was s plus 5, then because it was s plus 5, I have to write s plus 5 as s plus 3 plus 2. And so in short, we have to write our function in such a way that we can use the formulas for inverse Laplace transform. We consider one more example in which we will have that type of situation. If we observe here, in the denominator we have s square plus 2s plus 2, and we can directly decide that if last term is 1, then we will have square of s plus 1. So here I write directly, I rewrite 2 as 1 plus 1, and I observe that this is square of s plus 1, and here I keep s plus 7 as it is. Now because I am having square of s plus 1 here, I have to adjust s plus 1 in the numerator also. So for that I write 7 as 1 plus 6. Now I can rewrite this as s plus 1 divided by s plus 1 square plus 1 square plus 6 divided by this, but I write in this way 6 into 1 divided by s plus 1 square plus 1 square. This is our function which we have written in terms of functions whose inverse Laplace transform formulas are known to us. So what I have done, first I have decided the last term must be 1, and then I write this as square of s plus 1 plus 1 square. Now I am not having s plus 1 here, so I write 7 as 1 plus 6. Then I write in this way s plus 1 divided by square of this, and 6 divided by s plus 1 square plus 1 square. Why I am writing in this way? Because I have the ready-made formulas for inverse Laplace transform of these two. Therefore, L inverse of s plus 7 divided by s square plus 2s plus 2 equal to L inverse of this. Here we have s plus 1, and if we compare with s minus a, we will have a equal to minus 1 and value of b is 1. And because we have s plus 1 divided by s plus 1 square plus 1 square, we will have cosine function and e raised to at. Value of a is minus 1, so e raised to minus t. Value of b is 1, so we write cos t. Plus 6 times, here also value of a is minus 1, value of b is 1, but here we have 1, so instead of cos we will have sin and e raised to minus t sin t, and we can take e raised to minus t common and we write this as cos t plus 6 sin t. So in this way we can decide inverse Laplace transform of this type of functions. Remember that this factor is of second degree and we cannot write this factor as product of two linear factors s minus a into s minus b. It is not possible to write in this way. So that type of factor is called irreducible factor. So if you have second degree irreducible factor in the denominator, then only you have to use this formula. In this also we can observe that we cannot write this as s minus something into s minus something or s plus something into s plus something. We cannot reduce it into linear factors. So in that situation only we have to use this formula. Sometimes it will be possible, suppose you have this type of function s square plus 3s plus 2. So we can see this s square plus 3s plus 2 can be, this is 1. So here s into s plus 2 plus 1 into s plus 2. So here this is reducible. S square plus 3s plus 2 can be written as s plus 1 into s plus 2. So in this case we will not apply this formula because I can further reduce this into linear factors. So if we have this type of situation, then how to find out inverse Laplace transform, that we will discuss in upcoming lectures. But for these two formulas you should make, you must be sure that if our factor is in this form s square plus as plus b, and if this cannot be written as s minus something into s minus something, if it is not possible to factorize this into linear factors, then only use these two inverse Laplace transform formulas and try to find out last term and try to write down your function in this form. Okay, fine. So I stop here. I hope you like this lecture. Thank you very much.